All right, good evening, everyone. My name is Allison Thibodeau, and I am Chair of the Department of Geosciences, and it is my great pleasure to welcome you to the 21st Annual Noel Potter Lecture. Before I go further, it is important to state that we recognize that Dickinson College is located on the unceded lands of the Susquehannock Nation. We acknowledge the many indigenous peoples that lived on these lands, as well as the thousands of Western indigenous children forced into the Carlisle Indian Industrial School in 1879 as part of a federal cultural eradication effort. The Potter Lectureship was established by alumni, colleagues, and friends in 2004 to honor Emeritus Professor Noel Potter, who retired in 2005 from Dickinson. George Lee, from the class of 1971, led the charge to raise a generous endowment from fellow alumni to fund this annual lecture in honor of Noel's 36 years of service at the college. During that time, Noel taught 3,178 students in physical geology and 233 in field and structural geology. Noel, if you could please stand. And now I am privileged to introduce our 21st Annual Potter Lecturer, Dr. Jesse Reimink. Jesse is the Rudy L. Slingerland Early Career Professor in the Department of Geosciences at Penn State. It is worth highlighting that Rudy was a Dickinson student who graduated with a geology major in 1969. In addition to his role as a professor, Jesse is also the director of the new Energy Transition Entrepreneurship and Innovation Cluster within the College of Earth and Mineral Sciences. He also co-directs the Lion Cron Geochemistry and Geochronology facility, where his research focuses on the formation and evolution of continents, understanding magmatic and hydrothermal systems, and developing new geochronological and geochemical tools to refine our understanding of outstanding petrological problems. Prior to joining Penn State, Jesse was a postdoctoral fellow at the Carnegie Institution's Department of Terrestrial Magnetism. He earned his PhD in the Department of Earth and Atmospheric Sciences at the University of Alberta and has a Bachelor of Science in Geology from Hope College. We are honored to have Jesse here with us today. The title of his talk is How Does the Earth Get Distilled? The Reawakening of Geosciences in Society. Please join me in welcoming Jesse.
Okay, we're on. Thanks very much. This is a great honor to be here. And one of the benefits of being at Penn State, as you can probably tell, is you get to make up your own titles. So you can have a whole bunch of different titles at Penn State. I'm really excited to talk to you about, as you can probably tell, this is going to be a fairly experimental talk. And so I'm experimenting on all of you and trying out some turns of phrase, let's say. The first part, I'm going to focus on some research we've been doing that focuses on how Earth's continents became stable and distilled and stable, and those two things are intimately linked together, and we'll work through some of the science story there. And I think it's a good example of why I'm really excited to be a geology professor at this current moment in history. And so the latter half of the talk I'll work through trying out some ideas about why I think being a traditional geologist, a geoscientist in this day and age is a really, really exciting time period. This is a picture from field work up in the Northwest Territories in the Acosta Gneiss Complex. I've also got some rocks here that we can come and look at. Maybe I can pass them around. So some of Earth's oldest rocks, 4 billion-year-old rocks here from the Acosta Gneiss Complex. You can come up and hold this later. But this is what a stable interior of a continent looks like. It's not a lot of topography. It's been hovering right around sea level for hundreds of millions of years, if not billions of years. And this has been stable. Not much has happened here for 2 billion years or so. So we're going to talk about why that might be in various hypotheses. But I want to focus on what do I mean by distillation first. This is a funny photo from one of the breweries around Penn State that I pulled from their website. I found quite entertaining. But we're really just talking about distillation here. We can talk about maple syrup. We can talk about alcohol, ethanol. It's simple distillation. How do we relate that to the Earth? What do I mean when we talk about this? And igneous petrologists, which I'm one of that breed, usually think about distillation in the igneous system. So this is what we kind of learn in the intro physical geology class. This is from an intro level textbook. We have the mantle down here that's ultramafic. The Earth does not melt, the Earth partially melts, and that partial melting is a distillation event. So the mantle wells up here, that decompression melts, and we form mafic oceanic crust. That's one of our bimodal types of crust on Earth. That oceanic crust in the modern world dives down as a ducting plate, brings water down with it, melts the mantle down there. This is a little bit inaccurate, but we get another distillation step there and broadly form intermediate crust in volcanic arc provinces. Really, we form basalt and something more felsic, but it's in bulk intermediate. The question I'm going to focus on today is how do we get this felsic stuff? How do we get true granites, real granites, in the interior? When we smash continents together, we do another distillation step. And so this distillation is important for a geochemist because we do things like we enrich in silica, aluminum, sodium a little bit throughout all these processes. Some of these processes do massive enrichments in a variety of elements that really matter to us, especially in this energy transition landscape we're going through. The rare earth elements, a lot of these are deemed critical by various governments around the world. So distillation is important, distillation is interesting, and there's some big unsolved problems when it comes to Earth's distillation. This is from Tamara Carley, professor at Lafayette. I just pulled this photo from her website when I gave a talk up there, and it's a beautiful representation of distillation. This is zooming in on her hand here. These are rocks from Iceland. We're showing distillation in Iceland. Iceland's kind of internally distilling itself, producing felsic rocks here of small volume, small extent, but it's doing it. It is doing that process. How does this work at a big scale, and is this stable? That's kind of the question. Okay, so I'm going to just briefly set the stage here. I like this view of Earth history. So start at 4.6 billion years ago, 4.568 billion years ago, and we work our way forward here. I've forgotten the vast majority of the things on here. I had to memorize them at one stage in my undergrad, but I've forgotten most of them. So, you don't have to remember, at least for me, what the difference between the Jurassic and the Triassic is, because frankly, I don't remember the numbers either. Because I focus on this early time period here. And 4 billion years to 3.8, the Hadean, the Archean. We're going to focus here for this talk at the end of the Archean. There's some really interesting changes in the rock record at the end of the Archean. And so between 3G8 and 2.5 is where we're going to focus. Here's a cross-section, highly schematic cross-section through an Archean craton. This is based on a place called the Slave Craton in the Northwest Territories that I've worked on for a while. I'll show you some rock photos just to kind of get everybody familiar with what the rocks look like. I think that's kind of an important framing. We have down at the bottom what are called basement gneisses. These things are igneous rocks that have been metamorphosed, deformed. They're now toothpaste rocks. Some of them go back to 4.02 billion years. The Acosta gneiss complex here. Let's pass this around. How about that? Acosta gneiss complex, 4 billion year old rock right there. It's in this basement gneiss complex. Whole range of ages. There could be a billion years of age difference between this unit and that unit there. They're all squished together. On top of that, we have this cover group sequence. Quartz pebble conglomerates are probably one of the more famous rocks in here. This is an example of one. This is probably one of the more famous rocks in the world, the Jack Hills conglomerate. Holding this rock, you will be holding 4.2 billion year old zircons. Some of the oldest mineral grains that we have on Earth are in that rock. It's a similar analog in Australia to this rock unit here, which is very interesting. But they sit on top, classic cover group sequence of sedimentary rocks. Of particular note in the Archean, we get fuchsitic quartzite, this really nice chrome-rich mica that creates this green color to it. Hard to see with this light, but that's in there. Banded iron formations are found in this area as well. And we get this package of sediments. Above that, we have pillow basalts. And the old term for Archean crustal blocks was granite greenstone belt, and this is the greenstone and granite greenstone. We know that these were basalts that were erupted subaquously into the ocean because of the pillow structures. These things formed by flash freezing of the magma around these rinds due to interacting with water. So pillow basalts in this particular part of the world 2.7 billion years ago. We move up on a skip some of the felsic rocks, or some of the volcanic rocks in this stratigraphic column. There's unconformities in there. Regionally, it changes a bit. Importantly, we get sediment packages. Relatively thick, kilometer-scale sediment packages. And here they're turbidites about 2.65 billion years ago. This one's metamorphosed. See some nice starlight crystals in there, and a luni there for scale. My PhD supervisor was Indian by birth and American by immigration status. So living in Canada for a long time, he forced me to never have the queen side up of the Canadian coin. He always had to turn it over and take pictures of the backside because he did not like the royalty. Anyway, so that's why you can see the loon. It's actually a better photo too. So turbidite sitting on top of this. And then at the end, here's a cross-section through this craton. The important part here is that the colors broadly match So basement gneisses underlie everything. We have this basaltic layer in here. We've got some sediments in here, thin layers of sediments, and then these blue and pink things are late granites. So the whole thing is intruded by granites and the late Archean granite bloom. In this part of the world, 2.6 billion years ago, 2.58 to 2.62 billion years ago. But these are beautifully preserved granites. They look like you're walking across the Sierra Nevadas. Nothing's happened to them since they formed. So this is the sign of a stable craton. Nothing's happened for 2.6 billion years. This is a stable block, a fully distilled block of continental crust. This is what the map looks like. All the orange is Archean granites. All the green, all the gray is sediments. All the pink is the basement gneiss complex here. Tomorrow I'll talk a little bit about the basement gneiss complex and finding old rocks in that. But I just want to convey to you the amount of granite in these areas is massive. Huge amounts of granite. That voluminous magnetism in this area, and that's part of this distillation process. So how did this happen is what we're after. Interestingly, and to add some more buzzwords into this talk, these are a critical resource. There's lithium, cesium, tantalum pegmatites that occur for the first time in Earth history are preserved in these areas. This is an example of one. Tungsten tin granites start to come on into the rock record. These are highly differentiated granites. These are granites that are undergoing high temperature metamorphism and forming from deep melting. So economic resources start to become abundant at the same time as distillation, as this final continent distillation. We're going to talk about why that happened, okay? So I'm going to zoom out and talk about some other geochemistry here. This is, I'm going to move quickly through this and only point out the parts that actually matter. This is kind of a complicated paper figure we put together from a recent publication we had. What this plot is showing is all of igneous rocks, all of the higher silica igneous rocks in Earth in a big compilation. I forget how many now. I should look this up. I think it's in the hundreds of thousands of analyses in here. And now what I've done is I've grouped them by age bin. So every age I put a bin in there. And then what you're looking at is the distribution of potassium to sodium ratio. So the orange ones are high potassium granites. Lots of potassium, more distilled. You can think of it that way. The greenish ones are high sodium granites. These are more like arc magmas that you get. A little bit more juvenile, a little bit less distilled. And so we can see in the earth, we've known this for a long time, since the 60s, since we could date rocks, really. We've known that the Archean record, that is basement gneisses, the gray rock that's going around, these are sodic granitoids. These are more juvenile. And only in this cratonization interval do we start to see, if you kind of squint a little bit, you can start to see that we get potassic granites occurring in large proportion in this interval, and those continue on for the rest of Earth history. So distilled is up on that plot there. Less distilled is down. This occurs in different parts of the world, this occurs at different times. So if we break this apart by cratons are blocks of crust that are a single geological area. The Slave Province is up here. What I've shown is the blue color here are these sodic granitoids. We call them TTGs. Doesn't matter what that means. They're the sodic things that dominate the early record. So we have this long record of TTGs. Then 2.6 billion years ago, we have potassic granites and perluminous. These are melting of sediments. Perluminous means sediment is melting into it. So we have boom, 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 cratonization, distillation. Superior Province, same thing. TTG record, then boom, cratonization. Amazonian, Pilbara, Kapval, bunch of cratons, bunch of different continents, all have a similar process, but different timing, and the timing is all in this cratonization period. So what's special about this cratonization period is kind of where we're headed. We put on here high temperature metamorphism. So high temperature metamorphism means we're putting heat into the crust, and we're putting more heat into the crust than typical metamorphic packages might have. So we're getting to high temperatures, which I'll talk about what that means a little bit later. But we're dumping heat into the crust. That is related to the magnetism. We have to generate partial melting somewhere, which is heat added to the crust, so that makes sense. What we'll talk about here is, what I'm showing here now, and the brown ones are sediment deposition, so sediment basins. And if you thought that continents would stabilize, then create high mountains, and then sediments would erode and you'd get basins forming, this is the opposite of that. We see sediments predating the granite record. And not all these are like really super mature sediment basins. Some of them are greywacke, but it's like a kilometer or more of sediment in one area is kind of what's mapped on here. And this is really the first time in the rock record that we start to see sediments preserved in large mass. This is a weird plot, but this is a global compilation of just sediment samples, and I'm just plotting a moving average of the number of samples in any age window. And so basically, the point here is that either fine-grained clastics or all sedimentary rock samples in this database, we go from very few in the tens to dozens maybe, to this interval where we get into the several hundreds of samples at this granization window. So we're starting to see sediments preserved in the rock record. Interestingly, that number of sediments kind of is the same until the middle of the Proterozoic. So we start to see sediments preserved there. Speaking to continents, weathering and continents becoming prevalent. Distillation, highly differentiated pegmatites, kind of late-stage distillation, again, occurs right around that interval related to the granites. So we're seeing distillation happen a little bit. The question is, how does this happen? And are these different rock units at all related together? Various people have tackled this problem. This is just a little bit of a high-level summary of various models. We have a very sort of modern style interpretation, collisional tectonics. Basically, take microcontinents, smash them together, and you get all this melting. So one model is this is just the natural, continents are just naturally growing and running into each other, and you're getting melting. Another one is subduction. That's a great way to add heat to the mantle. You have a subduction zone, melt the mantle, dump heat into the crust. All that magma is bringing in heat into the crust, and you can melt the heck out of it and generate basically a craton that we see today. And another one is a plume. A plume is a great way to bring heat into the crust. Iceland, any oceanic island, hotspot you want to pick. Hotspot volcanism is a great way to bring heat really high up into the crust and do all this melting. We're going to add another model to this, another potential model, which I think might fix some of the problems that we see with some of these models. All these rock changes that I talked about have led to kind of a prevailing, I don't know if it's a consensus view, but it's certainly a prevailing model that Earth has undergone tectonic transitions in its history. That in the Archean, so this is 4 billion years ago here, going to the end of the Archean, so this is all the rock record changes I showed you occur in this 3 to 2.5 interval. And then, we have supercontinent cycles throughout the rest of Earth's history. This is just a summary for Palin and Santosh, but there's a whole bunch of papers who have proposed that basically in the Archean, the Earth had some stagnant lid tectonic regime. A single lid. There was no mobile lids. There's no lids moving around. Lithosphere was not running into each other and breaking. But we had something like Mars, or it depends who you ask, maybe Venus, this was a stagnant lid planet. And then the global onset of plate tectonics is represented by this rock record, all these changes. That's a prevailing model. I wouldn't say everybody agrees with that, but it is a model that you'll see a lot of papers eschewing to this model. However, we need to consider something else that's happened in Earth history that we think might have happened. There's this idea, I think, a potentially well-founded model that the Archean was a water world, that there were not continents emerged above sea level. So we might move from some stagnant lid planet. That's a number that could be any number in here 4.4 billion years ago, but you went from stagnant lid to a hydrated planet, had oceans. We know we've had oceans for at least 4.2 billion years. We had plate tectonics going on, but we didn't have continents emerged above sea level. So no weathering was happening, or not significant amounts of weathering. So what happens if we just start to do weathering and start to drive weathering? Because weathering is a way to distill the crust. So we have to think really quickly, brief interlude about how do continents stabilize? How do they distill themselves? What does that mean? Why are those two words related? Stabilization and distillation. This is a cross-section through the Arctic, basically, so the Northwest Territories to Nunavut here and then up into the high Arctic islands. This is compiled by some mantle geochemists, so it focuses on the mantle, but it represents what stabilization means. Underneath of most of the old Archean cratons that we have today is super thick lithosphere. So the lithosphere is the cold and crunchy upper layer of the Earth that if you bend it, it's going to break. Down here we have the stenospheric mantle that if you bend it, it's going to flow, so it flows around. But this is cold lithosphere, and it's very, very deep and very thick. The mantle beneath the crust is very deep and thick. The crust is still like 33 kilometers thick. As we move out to the margins, it gets thinner and thinner and thinner. So this is cool and stable. So what do we need to do to get that cool and stable? We need to deplete it. We need to distill it. So we need to move the really we're going to focus on heat-producing elements. Uranium has 2 isotopes that decay. When those decay, they create heat. Thorium has 1, potassium has another. When those decay, they create heat. So we need to take all those uranium, thorium, potassium, get them up to the surface so that that heat can get out pretty quick. If the heat's down here, it's like putting a heat blanket underneath of a big, thick comforter. You get really hot really quick. Same thing happens in the crust. So we need to cool it down, and cool makes it rigid, and we need to move heat to the top to do that. We talk about geothermal gradients. If you're interested in something very cool to think about geothermal energy supply and think about geothermal gradients and whether they're transient or real geotherms. But in this deep mantle, as soon as we have this thick lithosphere, it makes the whole crustal column cooler, which makes it stronger. So this is temperature and depth, and it maps onto this perfectly. So these deep lithospheric roots cool down the entire crust. At the same depth, the old stuff is cooler than the young stuff that has thin lithosphere. Okay, so underneath of an oceanic crust, that's a high geothermal gradient relative to underneath of, let's say, the slave craton. Very cold as you drill down. It stays cold for a long time because it's super. Okay, so differentiation or distillation, I'm going to use those two words kind of interchangeably. What do I mean by those? I'm going to think in heat-producing element concentrations now. So if I go back, we're thinking uranium, thorium, potassium, those are the heat-producing elements, HPEs. We can talk about the amount of heat that they produce is going to be this A value, and it's in units of microwatts per meter cubed. That's just in a given volume of rock, how much heat is produced by radioactive decay. Undifferentiated is going to mean same amount of heat-producing elements through the whole crustal column. Differentiated means we've moved them all to the top. We've distilled it. We've moved all of the heat-producing elements up to the upper layer of the crust. What does that mean? Rocks are really slow at conducting heat, so heat trapped down here will stay down here. We need if the heat's at the surface, it gets out to if it's up near the surface, it gets out to the atmosphere very quickly and gets away from the system, gets out of the system. So all the heat production at the top, put your heat blanket on top of your comforter, and it gets you less hotter than if you put it underneath of your comforter, or put it in your sleeping bag or something like that. Strength is related to this, so undifferentiated crust, this is crustal thickness now. Thick crust versus strength in units they don't need to really worry about. So strength here, strong is high, thick crust is weak. So the thicker the continental crust, the weaker it is. However, undifferentiated is weaker than differentiated at the same thickness. So if we move all the heat-producing elements up, basically the crust is stronger. So it's more distilled, it's more robust, it can survive it can survive tectonic interactions. We've known this for kind of a while. How do we think about heat-producing elements in time? Okay, so I'm moving to heat-producing elements. This is a calculation using the average upper continental crust concentration of uranium, thorium, potassium. That upper continental crust will produce 1.5 microwatts per meter cubed of heat production right now. Back in time, 2 billion years ago, there was more heat-producing capability in the same rock, just because radioactive isotopes have been decaying for the last 2 billion years. And it actually gets hotter quicker as we go back, because uranium really becomes the dominant force back in time. So we really have to think about uranium. Okay, so distillation, continental crust. How do we move heat-producing elements? We have to do melting, partial melting. We take a sediment that has uranium, thorium, potassium in it. We partially melt it and produce a perluminous granite right here. We're moving heat-producing elements. They get concentrated in this granite. So melting this sediment, partially melting the sediment, moves it into the granite. So that's how we distill these things. Okay, so what did we do? Well, we thought about this exercise. We said, okay, what happens if actually there's no sediments in the Earth's system? So let's look at the rock record. The rock record was dominated by, let's look at this little schematic up here. Let's just pretend that all the continents we had on Earth were submerged. There was no sediments around. And actually the rock record kind of tells us that. There's very few sediments preserved in the old rock record. If we look at the heat-producing element concentrations, I'm going to go back a couple slides here real quick, to this compilation here. If we look at the heat-producing element concentrations in the TTGs here, this global compilation, you can see there's not as much potassium in these rocks. So they're probably going to have lower heat production. They have less uranium, less thorium. Their heat-producing power is going to be lower. So if we go back in time, skip forward here, what we've mapped out here is heat production. This is just a probability distribution, so think of it as a histogram of granites in the Archean, high silica rocks, tonalites, granodiorite in the Archean. So the two different Archean rocks. This is from the real rock record, all of the samples that we have in a database. Very low heat production in basalts, we kind of know that. And actually pretty low in these TTG suite, these sodic granitoids. Well below what an average upper continental crust would be if we just took the composition of the crust right now and back projected it 3 billion years ago. Actually, substantially lower. So if we mix basalts with TTG rocks, that's kind of what we get. Now, If we take that idea and say, let's slam microcontinents together, let's double the thickness of this juvenile continental crust, what happens? We just say, let's take a layer that's 1.5 microwatt per meter cubed, let's stack it on top of another layer, like we're smashing two continents together. We can create a thermal evolution model that watches that thing evolve in temperature space. And this is what it looks like now. This is the best you're going to get for video in this talk. Geochemists make terrible videos. The geophysicists always make really beautiful videos, and they're talking. I'm always very jealous of it. So this is my attempt at making a little video. What is this showing us? This is telling us depth versus temperature. And this is we're watching, it's not really geothermal gradient, but we're watching the thermal state of the lithosphere evolve. We're watching the temperature through this crustal package. So we're basically saying we've stacked two plates on top of each other, taken the Himalayas, we're stacking two plates on top of each other, and we're just watching that thermal field evolve. So at first it goes from cold to hot at depth, and we've stacked cold to hot on top of each other. So it starts cold to hot, cold to hot. So the first thing you know is this is time over here going 0 to 50 million years. So over 50 million years, this is what will happen with this amount of heat production throughout the whole crust. Basically, it'll heat up really fast, really quick, but then it really slows down and it doesn't get hot. This blue line is the solidus, so we need to cross that line to do any melting. These black dots are Archean metamorphic, that high temperature metamorphic story we see. So these are metamorphic petrologists that put together pressure temperature estimates. So we're trying to achieve a line that fits through there, geothermal gradient that fits through that, to explain the data in the rock record. And this doesn't do it. If I look at percent of melt, in this model, we can calculate the amount of melting that happens down there. It just touches the solidus, so we get fractions of a percent of melting. The conclusion here is that TTG, this Archean continental crust, without any external heat source, is really hard to differentiate. It's really hard to melt and produce true granites from this stuff, unless you have an external heat source, unless you have a plume coming in or basalt coming in. So internally, very hard to differentiate this stuff. And this is kind of a surprising result to us. Now, what happens if we play this forward and say, okay, we actually don't have, now if we include sediments in the system, we know around 3 billion years ago we started to have sedimentary packages around. What's the heat-producing element power of a 2.5 billion year old sediment? Well, let's look here. We've used some principal component analysis to tease apart end member compositions. It doesn't really matter what these are, but shales are hot. We kind of know that. Shales are hot. Mafic rocks are cooler, don't have as much heat-producing elements in them. And the siliciclastic rocks in the Archean have some uranium, detrital, uraninite, things like that, and it make them a little bit hotter. But we're starting to get kind of hot rocks in this heat production capacity here. So these are approaching estimates for upper continental crust today, except projected back 3 billion years ago. Remember, things are always hotter back in time, so all these calculations are done back 3 billion years ago. So if we include sediments in our model now, let's say we start to have emergent continents, we start to do weathering, which is a very powerful distillation step on Earth, and then those sediments get down in the crust, they're like a heat blanket going under your comforter. What happens when we layer these 3 microwatt per meter cubed sediments, put a bunch of them down in the lower crust, and watch that thermal field evolve? Well, now all of a sudden, we've got the red line now is the sediment solidus, so the line at which sediment melts, the line at which TTGs melt, the pressure temperature gradient we're trying to achieve, and we're getting closer over 50 million years. And this thing's still moving at 50 million years, so we could kind of increase our model length and it would probably continue to evolve longer. But we get a load of melting in the sedimentary package. We get some significant, it doesn't look like this because the scale is huge, but we do get some significant melting of TTG crust down below. So if we start to have sediments in the system, especially back in time, we can do distillation a lot more efficiently. So the whole hypothesis, we've got a couple projects that are really testing this hypothesis in a more in-depth way using classic metamorphic petrology techniques, is that in an Archean water world, before continents emerged above sea level, it's really hard to differentiate. We can't actually create very stable continental crust back in time because the heat-producing element concentrations are pretty low. We can't distill the crust to the final granite or the final pegmatite distillation step. However, in a world where we do have continents and we do have sediment weathering off of the mountains and being dumped into big basins and being caught up in a tectonic cycle, that sediment is kind of supercharging melting. It's supercharging distillation. So if we dump sediment down into the lower crust, we can do melting in a way that we couldn't do before. And so exposed continents leads to weathering. Weathering leads to sediments, and sediments are a really powerful heat engine when we include it in plate tectonics and get it down into the lower crust. So, and then we end up with a differentiated, strong, stable crust. We have all the granites up top. From all this melting gets moved up to the top. All the heat-producing elements are at the top. We have depleted stuff down in the bottom. We see this in the rock record, the late Archean granites that I talked about on that map that showed you a map of that. These are all really high heat-producing element concentrations. And the metamorphic rocks, we don't have an extensive record of these from the Archean, but they are depleted in, these are the metasediments, in fact. So they used to have heat-producing element concentrations over here. Now they've been depleted in them. So we kind of see this process. And so melting is really the big thing, and we need to find a way to kind of drive melting forward here. So, okay, that's the story of distillation, especially for the Archean. This is very theoretical at the moment. We're coming up with ways, we're advancing ways to kind of test this model and see if this actually works, because it predicts a lot of sediment in the lower crust of Archean crustal blocks. A lot of sediment underlying stable crust globally, which we should be able to potentially go see. It's hard to see what the lower crust is, but we can work on it, and we can try and make some models for it. So sediments are really important. This is kind of an Earth system style of thinking about the surface environment. I used to kind of think, okay, sediments don't really matter. They're just hanging out on the surface. But they actually matter, and they matter more back in time. And they matter for continent stabilization. So maybe there's some Goldilocks interval in Earth's evolution where you could generate stable continents like this with this process, because heat-producing elements are more powerful back in time than they are today. Okay, so that's the science sort of conclusion point. But I think this is in part, this I think highlights the reason I'm really excited to be a geology professor. I'm really excited to be a geologist at this point in time. And as part of the work we've been doing with this, here's the podcast thing right there, we've had the great pleasure, we've created some audio-visual books as a part of this too, in a little app called the CampGeo app. It's a QR code that links to both of those things right there. As part of this, we've been really amazed by the level, the range, wide range of really insightful, expert, accomplished people who are just willing to sit down and talk to us for like an hour, hour and a half. And none of the ideas that I'm going to present in the next little bit, none of the pitch I'm going to give you is of my own creation. A lot of it comes from a lot of these people, other people I won't list here that we've talked to, that are very excited. There's this general enthusiasm for the geosciences that goes above and beyond the kind of normal. Geologists are always kind of excited about what they're doing. Geologists are passionate people generally, but there's excitement about the future in a way that I think is really interesting. You're starting to see, startups coming online, and it's a very exciting time. So what I'm going to do for the next little bit is give you 5 bullet points that I think are really important to think of, especially for students in the audience who are debating what they're going to go into and what they're going to focus on. This might be a big reawakening for the geosciences, the traditional geosciences fields. It's a great time to be a petrologist, I think. It's a great time to know some structure, but also to think broadly. So I'm going to go through a couple points here. Geoscientists are needed at a baseline level. Just if the world is not changing underneath of our feet, we're going to need more geologists in the future. The world is changing under our feet. Climate impacts on the surface, but the solutions, many of the solutions are down at depth. And when we go down deep, we're dealing with rocks. Geologists are good at, geoscientists are good at that. The answers are in the rocks. The rock record has done a lot of the stuff that we want to do in an energy transition. A lot of the reactions we want to have happened in the rock record, so if we just look at the rocks, they might tell us something interesting. Geoscientists think really differently, and then we need to encourage geoscientists as entrepreneurs. So this is the Horizons way of thinking of the world. This comes from Ian Stewart, one of the main UK geoscience communicators. And the way to read this is the black line is business as usual. This is time. So what's important now, the business as usual, the companies out there, the ideas out there, the training that's out there right now is going to become less important with time. Things are changing. Horizon 2 is an entrepreneurial horizon, so things that you could raise money for that will have an impact in the next decades. That's this version here. And then this is the long-term thinking. These are the visionary time periods where this is like this will be important 50 years from now. It's important for people to start thinking about, but it's not going to impact us in the next decade or two. So business as usual, entrepreneurial, and horizons. We'll come back to this. So number one, geoscientists are needed at baseline. There's a bunch of reports that have come out in the last couple of years. This is from one from the AGI, Geoscience Workforce, pulling data from the Bureau of Labor Statistics, saying change in employment in the geoscientists is positive by a few percent. It's around about the US average. So it's not necessarily a growing workforce at baseline. This is a little bit old now, but it's there. It's stable. There will be geoscientists, broken apart in a bunch of different dimensions here. But the point is that we're going to need geoscientists in the future. If the line of needs is flat and training is going down, if we're training less people, the people who are trained are more valuable. So this chart shows that those of you who are in geosciences now are going to be more valuable in the future because there's less of you. So when we have flat to increasing demand, and we have enrollment declines across the Western world. This is a bunch of different countries, UK, Canada, Australia, the US, the green line's the US geoscience undergraduate enrollment and number of students for the US, other ones over here, against the year 1970 to 2025. We have big peaks, big drops through time. We kind of know this if you're in geoscience education. This paper mapped on some different events here. All this is the price of oil through time. So this is like, you know, the peaks in enrollment here are generally thought to lag behind investment in oil and mining exploration. So students kind of follow the trend, but they're a couple years behind. The point here is you probably don't want a degree at the peak here because there's a lot of people graduating and the demand is probably going to go down. Where do you want to get a degree? Well, you want to get a degree down here because you're ahead of the peak. There's not many of you and you're ahead of the peak. You want to get a degree down here where there's a big peak coming, but there's not many of you around. And where are we right now? We're on this downtrend. There's not much debate that there's going to be an event 4 somewhere over here. The debate is what the magnitude of the event 4 is actually going to be. And I'm going to pitch over the next little bit. I'm extremely excited about the geosciences because I think H4 is going to be quite big, especially if we do it right. Here's some quotes from this, from some of this literature. You know, in Australia, it's the worst skills crisis in a generation. Geoscientists workforce will have a deficit of 130,000. You know, you can argue about these specific numbers, but the point is that there is, even if the world's not changing, there will be demand. Point number 2, the solutions are at depth. This is, you know, there are climate impacts or increased risk of climate impacts, let's put it that way, across much of the world. Geoscientists will be needed for these things. There's a whole new range of geosciences that is very interesting. In our department, you know, we've got people dealing in geoscience risk, and insurance companies will need geoscientists. You know, we have to deal with some rising sea level, landslide prediction, all these things. Even if the climate wasn't changing, this is becoming a very popular field for geoscientists to go into. So increased demand from these things. But also very importantly, and why I'm excited about my particular field, is that many of the solutions are at depth. And the depth could be like the next frontier. How do we know what's down beneath our feet as precisely as possible? Those are geologists that help with that. It's engineers, it's geophysicists, but it's also geologists and people who know the rocks. Their resource extraction at depth, lithium brines, ore bodies, 3D modeling of these things, carbon sequestration, hydrogen, geothermal energy. We'll focus on a couple of these here for just a couple slides. This is a map from Visual Capitalists based on some research by Benchmark Minerals that just shows in a visual sense. I really like Visual Capitalists. They kind of pull things together. Sometimes they're a little bit biased based on who's, you know, helping them with the plot. But copper mining in the current supply versus the excess needed in an energy transition in 2030. So this is not too far in the future. We're going to need close to 300 new mines for the copper. Copper is, what does that say? I'll read it to you. 61 copper mines, estimate excess copper mines. Phosphoric acid, we're going to need more nickel, graphite, lithium, graphite, manganese, cobalt, nickel, etc. I said nickel already. We're going to need more mines. We're going to need better exploration tools. This is only 2030. If we play this out in the future, this is some work by Larry Cathles and Adam Simon. If you play this out over longer time horizons, we're going to need more copper. This is sort of historical production, and historical production will probably go in the other direction pretty soon if we don't start finding more. If we want net zero stuff, these are massive extrapolations, so I don't want to focus too much on the numbers here, but these are all up into the right demands. For copper, copper is kind of the artery for the energy transition. We need copper in a lot of stuff. We're going to need a lot more of it. And mines are getting long. It takes longer to open a mine today than it has ever. So we need to get on this now if we're going to answer some of this demand in the future. Or we're going to have to think about our solution set. Really interesting plot here, again from Visual Capitalists in partnership with BHP. This is a map from 1900 to 2020 of major copper discoveries against depth in meters. The size of the discovery is the size of the circle. So you can see these are very shallow and very big. Recently, they've gotten smaller and deeper, which means harder and more expensive to find. They're smaller and they're deeper. all these discoveries. Some of these are mines, some of these are not. Or copper mines, these are harder to develop, actually. So we're starting discovery and development, getting harder, more expensive in the future. We get deeper, we need geologists. BHP estimates a massive $250 billion US investment to overcome some of these. Okay, it's BHP, of course they're going to say that, but you know, these are big numbers we're dealing with here, big investments. What about geothermal? Geothermal is a great energy resource, probably maybe this Goldilocks energy resource if it can be done right. Here's a map of geothermal. This is actually, identified hydrothermal sites are in the dots here, and this is a deep geothermal systems, deep enhanced geothermal systems from the NREL, where red is highly prospective, and you know, the lighter colors are less prospective. Deep enhanced geothermal. Heat is stored at depth. I just gave a whole talk kind of talking about heat and movement through the crust and where it occurs and why it occurs. It's very interesting, very hopeful that this will be a reliable energy source for the future. What is enhanced geothermal? This is from the Forge project. It's finding an area where the geothermal gradient moves up, meaning it gets hotter quicker when you drill down. You drill down and you frack that area, engineered fractures, frack that hot, dry rock, take cold water, pass it through, and you suck up hot water. So we're engineering this, hot, dry rocks. Anybody, what's the metamorphic gradient? What's the metamorphic facies here? 200C, 250C, some depth. Anybody know what the anybody taken metamorphic petrology yet and know the facies there? Wants to risk an answer? What's that? Yeah, prehnite pompelliite, right? We're up in here, prehnite pompelliite. A lot of the enhanced geothermal energy is moving up in temperature to higher temperature stuff. Like prehnite pompelliite and green-schist facies metamorphism has never been popular. Like metamorphic petrology is really interesting in these spaces. It's interesting reactions. You're fluxing fluid through hot, dry rock. You're going to do reactions. Fluid entices reactions. So this is an interesting space that we don't necessarily know a ton about. It hasn't been a field of a lot of study. And this is fundamental metamorphic petrology. There's some really interesting questions that we should be answering. And this highlights point number 3, that the answers are in the rocks in a lot of these solutions. Carbon sequestration, long-term carbon sequestration, is actually just making rocks. It's a very natural reaction. We're making rocks. This is a picture of a serpentinite, or a peridotite that's been silicified and carbonized. This is a super oversimplified reaction, but we take calcium, mix it with CO2, and create calcium carbonate. Okay, that's taking CO2 out of the atmosphere through the water, mixing it with calcium. How do we get the calcium? Well, we break apart calcium silicate. We can do the same thing with magnesium, olivine, and we create magnesium carbonate. So, a generalized reaction, we take CO2, bad, we put it in there and we make calcium carbonate, which stores it in a mineral. We might even get hydrogen out of this reaction. Hydrogen may be good. So serpentinization reactions are really interesting. The rock record has done this for us. It's very interesting, very exciting reactions. So if you know rocks, you know fluids, this is very helpful. You could get metal ions. I just heard about this from some petrologists have just sort of gotten a patent to this. You can think about different minerals. This is kind of an energetically difficult reaction in some ways to do. Calcium silicate pyroxene breakdown, kind of hard to do. There's some volume effects that are important to take into account. Maybe we use gypsum as a metal source and do the exact same reaction with some microbes. This has happened in the rock record. You can maybe try and start a business out of it. Like interesting stuff to think about. The answers in the rocks. Earth has done a lot of this stuff for us before. One thing that's come out of talking to a lot of people who've gone out into the business world, and usually not geoscientists who go work in the geoscience business world, but geoscientists who go work in other industries, is that geoscientists think differently about the world. And that's actually really powerful. And your training in geoscientists gives you a mindset that is different from many other fields. And this is a very blanket statement that's definitely not true in all instances, but in a general sense, there might be some accuracy to this. So why do we think differently? We think at scales that are just totally different than other fields. Astronomy is probably bigger, certainly bigger. But our scales are pretty big. We're talking about continents running into each other over thousands of cubic kilometers. We can't model these things in a computer simulation. We can't run experiments in the lab. We can run experiments in the lab, but we have to extrapolate 10 orders of magnitude out to get to the relevance to the Earth system. It's a huge Earth system that we think about. And we do this from an intro level. We show plate tectonic slides in the first class you take in a geoscience degree. So we start early on this. We think about time. We think in deep time, 4-dimensional thinking. Plate tectonics over 3 billion years. that's a really hard thing to wrap your head around, and just thinking about that and practicing that in a geoscience degree gives you a unique mindset about the world and a unique way to think about it. And I've met people in the business world who run hedge funds now who are like, I love geologists because they think about the world differently. Complexity, we deal in complexity. This is a photo from my work from the Arctic coast of Canada. That's a complicated rock. We landed in the float plane, we're like, oh boy, that's cool. We got to spend an hour and a half taking photos. It's so complicated. What do you do with it, right? This is toothpaste rock. How do you even start to think about this thing? We have to, as part of the job, we have to think about the natural complexity in rocks in the Earth system. We have a very rich data set. We deal in 3 dimensions. This is some picture from some modeling software startup company. This is drill hole data. So we're dealing in 30-dimensional data in 3 physical dimensions. So we get geochemical data from every point along this. We get a bunch of geophysics data from every point along this. We are dealing in very complicated multidimensional data sets very early on in the training system. And decision making, back in this rock, I mean, even a very simple one, I can only carry 5 rocks in my pack. Which ones do I grab when we're on this outcrop? Like, that's a tough decision that impacts my whole research program. Decision making under the face of uncertainty is a really, I think, something we're pretty strong. We're pretty good at. And this is how I'll summarize this last little bit with this tyranny of the discontinuous mind, this essay by Richard Dawkins. Basically, it says that the human mind is binary. I think we know this. We're seeing repercussions of this at the moment. We love yeses or nos. We love high or low. We love safe or unsafe. Like, the world does not operate this way. The underlying world is continuous. It's not discontinuous, but like evolutionarily, we kind of are designed to think like this. We want to know, is driving my car safe or unsafe? Is the groundwater safe or unsafe? And it's not a binary. The world is continuous, and I think geological minds are continuous. Well-trained geological minds. It makes us adaptable, and it makes us we can think about different things, and we can make decision in the face of this continuous world around us, because we ultimately have to make decisions about things. Which leads me to the last point, entrepreneurship. This is a big kind of passion project for me. This is that same thing for me and Stuart, the same horizon thing that's just kind of highlighting. There's a bunch of words on here. You can look give this paper a read. It's an interesting one. But I'll focus on the blue entrepreneurial thing here, and I'll focus on 2 aspects. This is integration with business and economics. A lot of the alumni that I've worked with at Penn State or people we've talked to with the podcast are really focused on this. Like, we need to integrate business and economic thinking a little bit more into the Geosciences program and nature-based solutions there. So I've kind of hit that nature-based solutions one kind of hard. The answers lie in the rocks. Here's a bunch of, these are just some of the high-profile companies. There's many, many, many companies that are starting up in this energy transition space. Many of them will fail. Some of them will be really big and very interesting. But nature-based solutions are an interesting space. This last, integration with business and economics, it's an interesting problem. Why are the geosciences not more entrepreneurial? Why is that not part of our brand? Because we have a lot of entrepreneurs. There's consultants. I think geoscientists are kind of a little bit risk takers, explorers. Research is a very entrepreneurial endeavor. You're going out into the unknown, don't know if it'll work. There's a branding problem, though. I just typed into ChatGPT, show me a picture of a geoscience consultant and a geoscience entrepreneur, and I think we have a branding problem, and I think that's kind of clear here. Like, we need to work on this. There's a problem here in the way that the world sees us as geoscientists. And the NSF and AGU and GSA have issued a couple reports on this, so kind of worrying why entrepreneurship is not part of the brand of geoscience. So there's a report by AGU in partnership with NSF, and the same thing for the GSA in partnership with NSF, kind of summarizing public opinion about why this is the case. Here's a bunch of reasons why geoscience and entrepreneurship are not more linked together. And I think some interesting ones are the culture discourages business and applications. There's this kind of mindset of academic versus entrepreneurism that are kind of at odds with one another. Maybe even an internal conflict within ourselves between the extractive industry and social responsibility. A lot of potential squishy reasons why this is the case. They present some potential solutions to this that kind of focused on the funding side of things, like how to get these things off the ground, but rebranding geosciences is kind of an important one that you'll see a bunch of this, increase public awareness, business knowledge and curriculum, foster entrepreneurial mindset during training. So there are some solutions to this that I think are pretty exciting. But to me, the future is very bright, and if we focus on this blue entrepreneurial horizon, I think there's a ton of space for people who know rocks, who think about the Earth in a particular way to go out there and make a difference in this blue horizon here. So I'm just extremely excited for geosciences as a whole going forward, and that's the end of my experiment on you. So I'd love to get some feedback. So thanks very much. I'm really honored to be here talking to you. Thank you. Which one? Both of them?
Wow, what a group. It really makes me feel good. I see my replacement in this room. And early in my career, I was in borehole geophysics before I became a colleague of Dr. Knoll's wife, Dr. Potter's wife. And you were talking about uranium, thorium, and potassium as ancient, and yet in borehole geophysics, that is extremely important because that's how you differentiate between different types of rock.
Yeah.
And it is radioactive, and people don't realize that. You can hold like a Marcellus shale in your hand, it won't hurt you, but I wouldn't eat it because it is.
Yeah.
It is. But even carbon sequestration, where we were working at the Geological Survey, and all the different solutions. And it's all the easy stuff is found already. It's harder to find the new sources of. If you're out in Utah, go visit the Bingham Mine. It is spectacular.
Yeah.
But I'd just like to thank you for this because this is very encouraging to see all these young people here.
Yeah, I agree.
It turned out.
Absolutely.
I can retire now. So.
You're in good hands. Yeah.
That was a fantastic lecture. Thank you for joining us. If you could give advice to your undergrad self, what would you tell them?
Oh, my undergrad self. I think that's a really good question. My undergrad self was pretty casual, if I can say it in that way. I think it took me a long time to get serious. I always kind of liked rocks, so I was always kind of serious about liking rocks. It took me a while to really sink my teeth into understanding rocks and thinking broader about the implications. So, this thing here, the fact this Horizon 2 thing and like rocks as, a business venture, it took me a while to link those together. I'm still doing it right now, still trying to work through what the future might look like here. So my undergrad self, I would say listen more. Just be quiet and listen more to other people, and also don't be afraid to dive deep, because I think I kind of hung around the surface a little bit. And the only way you're going to be successful is by going deep and knowing how to take yourself into some depth. Learn thermodynamics, because it's going to be important. Or think about things that are hard. That would be the advice to myself. It's a hard question, but thank you for it. I hope I've answered it well. Yeah.
How do we balance the need for all these strategic minerals for the energy transition to net zero emissions with environmental regulations that are pushing a lot of exploration and production to other countries that don't have as rigorous environmental regulations?
Yeah. Well, if I were president for a day, no, I don't know. I don't know the answer to that. I think this is the conversation, though. I think this is the conversation for the generation that's sitting in this room. It's going to be about, you're going to have a societal discussion about the grid, where we get our materials from. Do we want to continue to strip mine the Philippines? I mean, that's exaggerating, but where do we want to get our nickel from? Is it better to get it from some other country where we don't have the environmental impacts? We could do it cheaper, or do we want to do it locally, a little bit more expensive, but do it environmentally in a way that our regulations force us to? And are the certain regulations necessary? I mean, it's a big societal discussion. But I think we need to have it. And I'm encouraged because it's starting to happen. I mean, I see these articles that are actually about geology in the front page of the New York Times, the Wall Street Journal, all these, they're on the front page actually, which is not happened in my career, and I'd be curious to know if it's happened in your career. I think it's helpful because the conversation's starting. But we have to come to it from an informed point of view, for sure, and have a nuanced discussion about these things, because it's complicated. It's not an easy answer. That's my 2 cents on the matter. But you think about it for yourself. You should be thinking about these things. Like students in the audience, think about these things. Oh.
In my career, got a partial answer for your question. In my career, which was 42 years with the Pennsylvania Geological Survey, and school and grad school before that, stories on the New York Times front page that involved geology were environmental. They were coastal erosion or landslides or things like that, not resources. Mm-hmm. The resource emphasis is new.
Yeah.
When we hear that, certain politician wants to trade Ukraine for half of their resources, most of which are in the territories that the Russians are claiming, that gets kind of important kind of fast.
Yeah.
So anyhow, but partial answer to your question, in my career, I haven't seen resource stuff other than petroleum.
Okay, yeah. That's my sense, but I don't have the career longevity to answer the question that way, so.
Jesse, I had a question about that. Going back to the first part of
the
talk. With your model for the stable craton,
mm-hmm.
there seems to be a bit of a chicken or the egg problem.
Yeah.
In the sense that you have to get somewhat of a stable craton to produce the sediment.
Yeah.
It's going to then drive the melting to produce the stable craton.
So I think the question is, how do you go from this to this without stable continents? Right. How do continents become emergent without being stable? And that's a really important question. There are multiple hypotheses for this Archean water world thing. Like how did it go from water world to emergent continents? We know that there were continents around. Like I don't know the numbers off the top of my head. By 3 billion years ago, we had like 10% of the continental crust, maybe 5% of the preserved rock record is that age. So we know that there was some fraction of continental crust there. It was likely much of it was submerged. Those pillow basalts kind of tell us they erupt through the basement gneisses. They are underwater. So there's some emergence thing going on, we think. The question about how do you get continents emergent? There's a couple different knobs to play with there. There's some work that's modeled the mantle thermal state and what happens to a slab as it goes down, and says when you're hotter, you can't take water down as much. So ocean volume back in time was higher. So you could sort of drain the oceans into the mantle a little bit, or soak up some water into the downgoing slab. Maybe you could just grow continents. You could get larger continents that still don't have as much stability, and then they start to poke above sea level. You can cool the mantle to support hot topography. So it could have not much to do with the continents themselves, the crust, but more to do with the mantle. So there's like a bunch of different knobs to turn that are not related to continental stability or continental distillation. Distillation is certainly a knob. Like if you and that's the kind of the typical model, or the typical way of thinking about it, is that you stabilize continents, they then poke above sea level, then you get basin development. But I don't think the rock record bears that out, because we do have, we start to see clastic sediments. Maybe these are like, arc-clastic, basin formation type things, but they're there and they're preserved before the granite blooms. So it is a chicken or egg, and I'm not sure exactly which one came first. There's a bunch of different ways to play with the parts of the system here, though. It's a really good question, and one I don't have a great answer to, so kind of beating around the bush. But I don't have a great answer to it, and it's be really interesting, I think, in the coming years to hear different ideas about this.
So we're kind of unique for a small liberal arts college. Not that we have geosciences, because that's a core of a lot of liberal arts colleges. A lot of professors went to liberal arts colleges, like Hope.
Yep.
But we also have a business department, so you can get a business degree. I don't know if we've had a double major in business and geosciences yet, but we certainly recently have had a couple of geoscience majors go into business.
Yeah.
And so how, and maybe this is out of your depth a little bit as far as your major, but I mean, would you encourage geoscience students to take business economics?
Yeah, I would. There's a couple reasons for why. First off, we've just started spinning up at Penn State. There's an entrepreneurship minor program on campus, and the way this works is you take a couple courses in entrepreneurship and business, 3 courses, and then you take 3 courses that exist in a different college. That's your like specialization. They call them clusters, and they exist in biotech or hospitality or media relations. Our college did not have one, and I just started one up. So now you can get a major in geosciences and a minor in entrepreneurship innovation in the energy transition cluster. And the reason we started that is that a pretty overwhelmingly positive signal from alumni that that's a powerful combination. Students should go do that. That's going to be popular. Whether that's right or not, we'll see over the next couple years, but I'm hopeful that this combination of skill sets is really valuable. The other reason I think that, getting that, just starting to think about business and economics and money is, I think the geoscientist skill set, like our dealing with uncertainty, I think our field maps really well into economics, like big, hard to model, complicated systems. The styles of thinking are very similar. So I think there's a lot of interchangeability between those types of things that make for, and the last point is that what I've heard from some people, which is not universally true, is that as a geoscientist, competing with engineers moving up into the management of various industries, the engineers have a leg up to the geoscientists in part because of the business sort of thinking, that engineers advance into the managerial ranks easier than geoscientists do. And so just having a couple classes, you don't really need an MBA probably, but it might help, but like having some exposure at an early phase to business decision making might help you move up into the managerial ranks quicker as opposed to engineers maybe. I mean, that's all anecdotal, so don't hold me to any of that, but it's just my thoughts on that. So I think it's a good time to make that combination, but that's just me.
All right, well, thank you so much.
Thank you, appreciate it.